Now we would like to talk about the various operating modes of a MOSFET. So we have seen the structure of a MOSFET. Before we talk about the operating modes, we need to label the biasing conditions. Okay. So we have these four terminals. We can talk about the voltage in each of the terminals. Okay. So gate voltage, drain voltage, source voltage, and bulk voltage. Okay. Typically, what we do is we take source as a reference. Okay. So what we will refer to is VGS. Okay. So this is typically what we will use. So what we end up doing is we ground, let's say, source here. Okay. In case of a NMOS device, we ground the source, and then we talk of the gate voltage related to the source voltage. Okay. So this I'll call as the gate bias. Okay. Gate bias, and then VDS is basically drain bias, and we could also talk of VBS, which is you can apply voltage to the bulk also. Okay, that has some interesting implications. We will talk about it later on. So this is basically uh, body bias, you can say, body bias. But right now, in the initial discussion, we will take VBS equal to 0. Okay, initially, right now. Okay. If we don't say anything about the body voltage, you can assume that it is grounded for NMOS devices. Okay. So once you have this, what happens? You have essentially two voltage sources. You can change the gate voltage, you can change the drain voltage. Okay. So what happens when you change these things? So the first thing we want to ask is, what happens when VG is less than VT? Okay, is less than VT, let's say. What does it mean? There is no inversion charge. Okay. We may have depleted the MOSFET, we might have created a depletion region here. Okay. Before we do that, let's say, so this is a PN junction, right? So remember, there is always a depletion region here. So this would be a depletion region. I'm drawing it like this because it's an N plus device. So the depletion region will be mostly in the body. Okay. Very small amount should be in the N plus regions. There's a depletion region. Now, let's say I apply voltage, which is, let's say I'll write it as when VG is greater than 0 but less than VT. Then you end up having a small depletion region under the oxide as well. Okay, you have the depletion region like this. So now what do we expect in this voltage regime? Well, there is simply depletion, but there is no inversion charge. So there is no connection between the source and the drain. So do we expect any current? Well, ideally, ID equal to 0. Okay. Because VG is less than VT. But what happens practically? Okay. To understand that, we have to understand how how the current flows between the source and the drain, and we will do that by drawing a band diagram. We have been familiar. We have repeatedly talked about band diagrams, so by now we are very familiar with them. So what we will do is we will try to draw a band diagram from source to drain. So first I'll start with a Fermi level, which is uniform. Okay, I don't have any applied voltage right now. Okay, okay. Assume right now VDS is 0. There is no applied voltage across this. Okay. So how do we do? The recipe for drawing the band diagram is always very similar, same. So first draw the regions away from the junctions. Okay. So away from the junction, this is an NMOS trans N plus, so it will be EC here. There's, let's say, some band gap. Similarly, on the other side, there's going to be another semiconductor like this, right? And then in between them, well, there is a P-type semiconductor. Let's say, let me put it like this, right? This is how your semiconductors behave, right? So this is my source, This is my drain, and in between them is a channel region. So I'm drawing the band diagram across this, okay, across the channel. Okay, what happens now? How do we connect this? Well, we have to connect them in such a way that the bands, the band gap is maintained, right? And there's nothing much here. So here it should be connected like this, like this. On the other side, it should be connected like this. Okay. So now, if you look at this, how do the carriers flow in this structure? Well, here the electric field is, I'll say this direction, correct? Because it's a positive slope. EC is bending in the positive. It has a positive slope. Whereas here the electric field is opposite direction. The drain and the channels junction, right? Negative slope, so it's opposite direction. So how will the electrons move? Well, in this case, electrons will move back. It cannot cross. So electrons see a barrier. Similarly here, electrons will tend to go in this direction. So basically, what happens in this structure is electrons see a barrier, and therefore, and cannot rather, or cannot enter channel. Okay. But still, we always know that there's going to be some tunneling across the barrier and all that. There's going to be some tunneling. And so mainly what happens is the current that can flow is dependent on the barrier height. So this is my barrier height. Okay. So what we are saying is in an ideal MOSFET, if your gate voltage is below the threshold voltage, that is sub-threshold, we call it sub-threshold operation. So sub-threshold means Vg less than Vt. For an NMOS device, by the way. For a PMOS, we have to take the appropriate convention. So it will be below Vt in the negative sense. Okay, 0 to minus Vt. In between that, if it is there, it's a sub-threshold operation for a PMOS. Okay. So now, once you have this, in an ideal MOSFET, ID is 0, but in an actual MOSFET, in a practical MOSFET, shows ID not equal to 0. 0 due to current flow across the junction barrier, or across the, we call it thermionic barrier, right? Across the junction. It's also called as sometimes thermionic. Okay. So in this sort of a structure where you have this barrier, the current flow is basically exponentially dependent on gate voltage. Okay. ID exponentially depends on Vg. This is an important characteristic. We will actually, so it reduces exponentially with gate voltage in this case for a NMOS device. We will talk a little bit more in depth when we show you the current voltage characteristics. Okay. So right now, I want you to understand that whenever your gate voltage is below the threshold, there is small amount of current. Okay. Ideally, it should be 0, but usually it is a small amount of current. Okay. So the device is off, right? So basically, sub-threshold implies MOSFET is in off state. Right? Is a sub-threshold. Well, now what happens if you increase the gate voltage above Vt? Okay. So now, let's consider a situation where I'll say VGS is greater than Vt. What do we expect? Well, I didn't show you all the voltages, but anyway, now we understand what is this, right? This is source, and we said this is usually grounded. Let's assume this also is grounded because VBS is 0. Let's say this is connected to a VD, or you can call it VDS. I mean, the source is 0, so VD or VDS is same. This is VGS. Okay. So now gate voltage is greater than the VT, so there should be an inversion charge. Okay. So will the current flow? No. Back to same question. Will current flow? The answer is it depends. It depends on the drain voltage. Okay. If VDS equal to 0, then essentially there's no voltage to make the current flow, right? You just have charges. Okay. So ID equal to 0. But if VDS is, let's say, like 50 to 100 millivolts typically, small voltage, okay? What happens? When you have VDS, which is a small voltage, then the current can flow, okay? And what will happen is, we will derive an expression for this, but when you have VDS is small voltage like this, we call it a linear mode of operation. Linear mode. The reason we do that is, if you let's say plot ID versus VDS. Okay. Initially, when there is no voltage, ID is 0, but the moment you start increasing VD, the current starts increasing. Okay. Since we have an inversion charge anyway, the VG has been fixed right, above VT, so there is some current. Depending on the gate voltage, it will simply flow. Okay. So we have basically, let's maybe call this as VGS1 greater than VT. Okay. So current increases. Now, if I increase the gate voltage, what happens? Further increase the gate voltage. For example, I make instead of VGS1, I'll make it even higher than VGS1. Okay. Then we are increasing the amount of charge here. So we are making more inversion charge available, so the current increases. So if I increase the gate voltage further, you might have a situation like this. VGS2 is greater than VGS1. So effectively, we are controlling the resistance of a MOSFET, and the resistance is, it's simply following the Ohm's law. Okay. So if you look at this situation, the resistance is simply going to be R linear, I'll call it. R linear is going to be simply VD by ID. VDS by ID. That's it. This is my resistance, right? So the resistance, as you increase the gate voltage, the resistance reduces, so you have higher current. Okay. So this is how current the MOSFET behaves. So basically, whenever you have VG greater than VT and VDS to be a small voltage, 150 to 100 millivolts, MOSFET behaves like a resistor and exhibits linear IV characteristics. Okay. So you can call it this, some resistance R linear. I will derive an expression for this in the next lecture, but right now I want you to understand the operation in a intuitive way. Okay. All right, we did this. So now we are able to turn on the MOSFET. What happens if I increase my VDS still further? Okay. So if you do that, VDS is large, then we enter what is known as saturation mode of a MOSFET. To understand saturation mode, what we have to do is okay, let's do this. So you have this to be grounded, this to be grounded. You have a VDS here, you have a VGS here, right? So what is the voltage from source to drain? Okay. So let's try to see if I can call this as my, I'll put this as x equal to 0, right? That is the edge of the source region, the junction between the source and the channel. That I'll call as x equal to 0. The other one I'll call as x equal to L. The question is, what is the voltage between the across the channel basically, right? So I'll call this as V of textbook uses I think X, so let's call it V of X. Okay, so this is simply voltage across channel. What do you expect it to be? Well, when VDS was small, it's almost equal. I mean, this is there's negligible change in the voltage. But the moment there is a large VDS, the voltage actually varies across the channel and takes a form which is something like this. Okay, I mean it also makes sense because at x equal to L, right, V of x equal to L should be equal to VDS, and here V of, maybe I should use it, V of x equal to 0 should be equal to 0, right? Source is grounded. So at the left edge of my channel, I should have 0 voltage. At the right edge, I should have a VDS. In between them, there could be a linear approximation. You could even do that, but it turns out it's not exactly linear. Okay, I'm not justifying why it is, but it's some sort of a quadratic behavior. And you have this voltage across the channel. Okay. So this is basically your drain. X equal to L means it is drain. X equal to 0 means source. Okay. Below x equal to 0, it's all source. Okay. Okay, there is a voltage drop. So what? Well, to understand that, we need to look at the inversion charge, the amount of inversion charge. Okay. So what we are having is, let's say an oxide, and there is a gate, VG. This is an oxide in between. Okay. So what is the amount of Q under inversion charge? So you have this sort of a structure, N plus, right? So what is the inversion charge? We assumed right now that Q inversion is actually uniform, right? Q inversion is uniform across channel. Okay, when VDS is small, okay, you just have a gate voltage and you're applying, bulk was at the same potential, so you didn't really have much of problem. But now what you're seeing is this voltage across this channel here, right? This is Vx. All right. So if you have a Vx like this, what happens? So the amount of inversion charge will vary across the channel. Okay. For example, at the left end, what is the what is the density of the inversion charge, right? So density of inversion charge. What is it dependent on? Well, it's proportional to how much gate voltage I have, right? But it's not just that, but it's going to be a function of X as well, okay? Because Vx, right, voltage at that particular, just below this, just below the gate oxide, okay? Why is that? You could think of the entire oxide as tiny, capacitors, mass capacitors, each of them having a different voltage on the second plate, The top plate metal, it's all uniform gate voltage. But in the bottom plate, there is it's a semiconductor which is depleted, so there's going to be some resistance. and we are now applying a voltage across across the channel. So there's going to be variation of voltage across the channel, because of which the density will actually reduce as you go towards the drain side, because Vx is increasing, right? So this Vx is basically channel charge, right? Channel voltage. So Vx increases as X increases. So Q inversion reduces as you go towards channel region, as you go towards the drain region, right? Similarly, you could think of, I mean, what exactly should be the voltage? We will have to analyze. We will do that in a moment, okay? So this is an important part. So if I have to draw the, okay, let's take an example, okay? Let's take an example, and let's say my VDS, okay, VDS equal to VGS minus VT, okay? I I choose this specific number for a particular reason. It will become clear in a moment. So if my VDS equal to VGS minus VT, what is the voltage which is applied across the capacitor? You know, at X equal to L, let's say at the drain edge, my voltage which is sustaining my Q inversion, right? Q inversion is going to be Q inversion equal to is, let's say, is proportional to Vg minus Vx. But now what is Vx? It is VGS minus VT. Okay. So now what happens is, if your voltage is above that, your, if your drain voltage is above VGS minus VT, then effectively there is no inversion charge at the drain end. Okay. You see, this is going to cancel out, and these are going to cancel out. And if you still further increase VDS, right? So this term will increase further. VDS is greater than VGS minus VT, then Q inversion is equal to be 0. Because the threshold is where you have Q inversion, but below threshold there is nothing, right? So essentially the gate voltage, the gate voltage, effective gate voltage becomes less than VT, and so there is no inversion charge. Okay. So this I can schematically illustrate by drawing a structure, which an inversion charge which is like this. Okay. What I'm saying is, okay, let me not change that. Let me do this like this. Okay. So as my VDS increases, there is a variation of inversion charge across the channel. Okay. At VDS equal to VGS minus VT, Q inversion is going to be 0 at drain, or rather at X equal to L. Okay. If you further increase VDS, what happens is, let me just draw the L. So this is my Q inversion. This is my X equal to 0, X equal to L. Okay. There is no, this is at VDS equal to VGS minus VT. But I further increase my drain voltage, then I'll have a scenario where I'll have it like this. This is my X equal to 0. This is my X equal to L. Okay. Why is this happening? This is it. VDS is greater than VGS minus VT, right? So VG, right, which is basically you need a voltage above the threshold voltage to sustain the inversion charge. Okay. So that becomes less than VT. And because of that, there's no inversion charge. So this phenomena is known as pinch off. Basically, the inversion charge, right, is pinched off. That's why we call it pinch off. Okay. So what happens when you have pinch off? Well, in this case, you will have, so let's say initially we have seen in the IV characteristics. So if you call this as ID, this is VDS. Okay. There is a increase. There is a linear mode of operation. But once, let's say, this is VGS minus VT. Okay. So once you cross that threshold, right, or this is a very, very special thing. We'll call it as VD SAT. So I'll give a VD SAT is equal to VGS minus VT. Okay. So this is VD SAT. VDS equal to VD SAT. Then your channel has got pinched off. Okay. So after that, the current cannot increase because effectively, even though I'm showing you in a, as if the charge is actually spatially non-uniform, it's effectively just the density of charge is less. Okay. So after that, there's no further charge that is being added by the gate. Because of that, the MOSFET enters into what we call as saturation regime. This is linear. So initially the current will be linearly varying with the drain voltage. But once we cross VD SAT, there is no further addition of inversion charge. In fact, the inversion charge is actually getting, for a small distance here near the drain. So physically it will be in this area. There's no inversion charge at all. The channel has got completely pinched off. There's no inversion charge. Because of that, the current cannot increase any further. So whatever is inversion charge here, that will cause the current to flow. Why will the current flow? Well, even though there is this inversion charge, there is some field here, right? There is a field here which is going in opposite direction actually. So electrons can still travel on this side, right? They will reach the drain. They will get drift, So in the pinch off region, drift current causes the carrier to go across that pinch off region. Okay, drift current is present. In fact, even in other, when you have current, you have inversion charge, it's still the drift because VDS is applying is supplying the overall electric field, which will cause the carriers to go from the source to the drain. Okay. So this is saturation. So now if I increase my VGS, so let's say this is at 1 VGS, okay. I'll call this as VGS1. Now what happens if I increase my VGS? Well, I'll still have the same inversion, same thing like this, but at a higher voltage, I'll start seeing saturation. Which is VGS2 greater than VGS1. So this is VDSAT2, then, right? This will become VDSAT2, let's say. This is VDSAT1, VDSAT2, like that. So essentially, you have the voltage at the drain voltage at which it reaches saturation will be higher because the VGS has increased. VDSAT is simply VGS minus VT, so it will increase. Okay, so you have a higher amount of current which is flowing through. So these are the three main modes of operation of a MOSFET. So the subthreshold regime, where ideally it is zero, but practically it is going to be exponentially dependent on the gate voltage. We will see the exact dependence later on. In the linear mode, the current is directly proportional to the drain voltage. In the saturation mode, where if you increase VDS, it's not going to lead to any change in the drain current. So these are the three main modes of operation of a MOSFET. Okay. So this is the phenomenological or qualitative explanation of various modes. We will actually derive the current expressions in the next lecture. All right. So I'll see you there. Thank you so much. Bye.